So in our last couple of videos, we have reviewed determinants. We used determinants to define a cross product. And now in this video, what we want to do is we want to talk about the geometric interpretation of a cross product. So if you look at this theorem here, and we're not really going to be taking any time to prove it, but if you look at the theorem, if we have two vectors, A and B, and we do the cross product of A with B, what we end up with is we end up with a vector that's orthogonal or perpendicular to both vector A and vector B. So you see vector A drawn here in blue, you see vector B drawn here in red. If I take the cross product between A and B, I get this vector that comes straight up off of the plane that the original two vectors sit in at a 90-degree angle to each of them. So I'd have a 90-degree angle here with vector B, and I would have another 90-degree angle here made with vector A. Now here's the thing, there's another way that I can end up with a vector that has a 90-degree angle or is orthogonal to each of the original vectors. What if I would have had the resulting vector coming straight down like that? How do you know whether or not the cross product between vector A and vector B gives you the vector that you see drawn here in purple or the vector that I just drew in orange? So when you carry out a cross product, you follow what's called a right-hand rule. And if you're familiar with dealing with electric fields or magnetic fields in physics, torque problems in physics, torque problems can actually involve the cross product calculation. For those of you that have done a little bit of physics before you've taken calculus. But if we think about what the right-hand rule says, it says place the fingers of your right hand along the initial vector. The initial vector for this cross product here is vector A. So if I place the fingers on my right hand along vector A, I need to place them along vector A using the orientation that allows me to curl the fingers on my right hand toward the vector that's at the end of the cross product calculation. The thumb on your right hand is then going to point in the direction of the resultant vector. So if I had my fingers along vector A, the palm of my hand would have to be facing this direction in order to allow me to curl my fingers toward vector B. What that's going to say about my thumb is that my thumb is going to be pointing upward out of that intersection between vector A and vector B. What if we changed the order of the cross product? What if we did this calculation? What if we did vector B crossed with vector A? Well, if I did vector B crossed with vector A, I would start with the fingers on my right hand along vector B. Now, let's say the palm of my right hand faces this direction. I'm not curling through the smallest angle toward vector A if I place the fingers on my right hand that direction. If I flip my fingers, though, and I have the palm on my right hand facing this direction, see how now I am able to curl. Now my palm is, I guess, kind of upside down almost here to sit along vector B, but if I curl the fingers on my right hand toward vector A, the thumb on my right hand is now pointing downward to this resulting vector. So we've said in some of our other videos that a cross product calculation is not commutative. There is a relationship between what you get when you do one cross product and then change the order of the vectors for that cross product. You get a resulting vector that's the opposite direction, same magnitude. These vectors should be the same magnitude. That's my fault for not drawing the purple vector and the orange vector with the same magnitude. But these vectors should have been the same magnitude, but they go complete opposite directions. So this right here, what we just computed at the bottom of the screen, this is equivalent, oops, I guess I need to enlarge that a little bit. This is equivalent to negative vector A cross vector B. Right, -1 times that initial cross product vector. So to determine which vector you get, once again, fingers on the right hand along the initial vector in a way that allows you to curl through the smallest possible angle toward the second vector, the thumb on your right hand is then going to point in the direction of the resulting vector. I'm going to click back to this screen here. We're just kind of providing a primer to these ideas and these calculations that should allow you to do what you need to do throughout AP Physics C. For those of you that are at the beginning of a linear algebra course or a multivariable calculus course, you'd probably be dealing with these properties quite a bit more than what I'm going to mention about them here. But if you look at this, the cross product calculation is not commutative, but it has the product known as anticommutativity, meaning you don't get the same answer when you swap the order of the problem. You get the opposite of that original answer. And that's what the geometry that we were just talking about on this screen kind of supports. So the one example that we'll do on this screen has the set of directions that ask us to find two unit vectors orthogonal to the given vectors. So if we do a cross product between these two vectors, we get a vector that's orthogonal to each of the originals. If I switch the order of that cross product, or if I just multiply the original answer by -1, I get a vector that's still orthogonal to the original 2. It's just going to go the complete opposite direction, right? So doing the cross product one way gives us one of these vectors. Multiplying that answer by -1 gives us the other, or we can, do the cross product from scratch again. Far easier to just multiply by -1. So in this situation, we're going to set up our 3x3 determinant to compute our cross product. The order that I did this in is vector A times vector B. You can tell that because I've got my standard basis vectors across the first row of my determinant. I have my components of vector A across the middle row, and then I have the components of vector B across the bottom row. So the determinant that I've set up and the answer that you see right here for it is vector A cross vector B. If we want to go ahead and compute that cross product, we're going to copy I, j, and k out as the coefficients of three 2x2 determinants. So to find the 2x2 determinant that I'm going to have the answer for multiplying unit vector I, I'm going to cross out the row for unit vector I, I'm going to cross out the column that unit vector I sits in, and I'm going to do the cross product, or not the cross product, excuse me, the determinant with the 2x2 components that I'm left with right here. So multiplying the main diagonal gives me -3. Subtracting off what I get when I multiply the minor diagonal gives me 0. -3 minus 0 gives me -3. That's the coefficient of unit vector I. When I get ready to build the coefficient of unit vector j, I'm crossing out the row with unit vector j in it, crossing out the column with unit vector j in it, and then I'm doing the 2x2 determinant calculation between the numbers that remain. So I'll multiply the main diagonal, getting 6. I'll multiply the minor diagonal, getting 0. 6 minus 0, obviously 6. The reason why we have a negative here is because if you remember the definition of a 3x3 determinant calculation, it's always going to be subtraction between the first and second terms, and then addition between the second and third terms. So this sign isn't from the determinant that I just found, which is +6. It's from the definition of a 3x3 determinant. We always subtract off that middle term. And then I need to find the coefficient of unit vector k. So same process, cross out the row, cross out the column, doing a 2x2 calculation with what I have remaining. Main diagonal gives me a value of 0 for that multiplication, and then the product of the minor diagonal is -1. Well, when I do 0 minus -1, I get +1, and you might have heard me just say a few seconds ago that that is always going to be addition from the definition of a 3x3 determinant whenever we go from the second term to the last term. So here is our answer for A cross B. Now this is a vector that is orthogonal to each of the original vectors because we did a cross product calculation to determine this vector. But what we want it to be is we want it to be a unit vector. So a technique that we've used a handful of times is to go from a vector that doesn't necessarily have a magnitude of 1 to a vector that has a magnitude of 1 but travels the same direction as the initial vector does. We basically determine the magnitude of the initial vector, and you see that's what I've done here. So I applied the three-dimensional distance formula, or the formula for the magnitude of a three-dimensional vector, right? Squared the x component, squared the y component, squared the z component, added them up, took a square root, got square root of 46. If I take these components, -3 for the x, -6 for the y, +1 for the z, if I divide those by this magnitude, here is a unit vector that travels the exact same direction as this vector does. Since this vector is the cross product between the original two vectors, I know that this unit vector travels the same direction as this vector does, and because it was a cross product vector that we started with, we're looking at it being orthogonal to both vector A and vector B. If I want to develop another unit vector that's orthogonal to each of the originals, I need the vector that travels the complete opposite direction of this one. So if I just multiply all the components of that by -1, or a much longer route to get to the same end result would be to swap these two rows, do all of the calculations again, and if you do that carefully, you're going to arrive at this result. Oh, sorry about that. Hopefully what we've talked about here has helped you come to understand how to interpret what a cross product result is going to be in relation to the original vectors. Got a little bit more practice finding a cross product, and then a little bit more practice turning a vector that isn't necessarily a unit vector into a unit vector that travels the same direction as the original. So lots of little pieces kind of came together within this final example. Hopefully that's helped.